Hey everyone, so in this next video we're going to talk about using vectors to prove some things about geometrical figures. So you're going to be dealing mostly with triangles, parallelograms, maybe a rectangle, maybe a hexagon, just different things. Before we jump in, I want to review some of the rules that we've talked about so far. One is that about opposite vectors. So if you have a vector like mn, that is exactly the opposite of vector nm. Or the triangle rule is if you have AB plus BC, that is going to be AC. Also remember that parallel vectors are going to be some sort of scalar multiple, like maybe a 3. So maybe 3 times QR would be equal to, I don't know, TU. And if that was the case, then vector QR would be parallel to vector TU. It would also be 3 times the length of TU. And then one more thing that might be helpful for us is the zero vector, where you start and end at the same point. This doesn't seem like it'll be that useful, but it actually is going to come in handy here. So let's look at 2 examples where we're using vectors to do a proof in geometry. First of all, we have a triangle ABC. M and N are midpoints of the sides AC and BC, respectively. We are supposed to do 2 things here. We're supposed to show that this segment here, MN, is parallel to AB, but not using like the geometry rules from freshman, sophomore year, using, freshman year, or maybe even 8th grade. We're using vector stuff. And we want to show that it's half of the length. MN is half of the length of AB. Well, we can do that actually by doing one thing. If we show that vector mn is exactly half of vector AB, that's going to do the trick. Because remember how parallel vectors, we just need to show that one is a scalar multiple of another, and that also shows you the size as well. Okay, so what I'm thinking is let's think about how we can write vector mn. We're going to start with vector mn, and we're going to show this. This is what we want to get. And we're going to think about ways that we could write mn. Well, I'm thinking we should write about the original 3 points of the triangle, that would be helpful. So if I want to think of how I can get from m to n, I could go this direction, and then I could go this direction. I think that would be helpful. So that would be the same as mc plus cn. So I think it might be helpful also, though, maybe I should show my work this way. I'll do that, plus cn. We typically work down when we do these. Okay, so the next thing is that I'm trying to show half of AB. Well, I need there to not be m's and n's in here. So instead of writing MC, I could write half of AC. That would be the same thing. And instead of CN, I could write half of CB. And we can do that because we know M and N are midpoints. So now I'm starting to see things come together. I see a half that I could pull out in front, and that would leave me with AC plus CB. And now I see this triangle rule being used here. It's got different letters, but this connecting letter works the same way this connecting letter does. So I could replace this AC plus CB with simply AB. And now we've proven it. We did exactly what we needed to do. We showed that it was parallel because parallel vectors are simply scalar multiples of each other. And we showed that it's exactly half of the length. So there we go. That's the first one. And let's take a look at one more. Again, it's dealing with a triangle, but we are asked to do something different here. They give us the midpoints L, M, and N of the sides of the triangle. So L is the midpoint of BC, M is the midpoint of CA, and N is the midpoint of AB. We want to show that the medians, that's what AL, BM, and CN are called, because they go to the middle. We want to show that those medians could form a triangle. And you're like, but they like overlap. So how can they form a triangle? Right? Like, how can CN, AL, and BM form a triangle? Because they're overlapping each other. Remember, vectors are movable. So if we redrew AL and then connected BM to it, and then connected CN to it, they're saying that if we did that, if we moved the vectors around to meet end to end to end like this, that they could form a triangle. Okay, that's what we're trying to show. Well, let's think about what that means. We want to start here and work our way around so that we end up back where we started. That is going to utilize this rule, the zero vector. If we can show that if we connect these three things together and we end up back where we started, that would make a triangle, because that's what makes a polygon, if you end up back where you started after all is said and done. So we actually want to do something like this. We want to get to that type of statement there. So let's see if we can do that. So the first thing I'm thinking is just to think about one of our medians. So let's think about AL. AL would be if I did AB plus half of BC. We're going to connect AL, BM, and CN together. So in order to connect them all together, I need to know what they are first. So let's do the same thing with BM. If I start at B and go to M, that would be BC plus half of CA. And lastly, Cn, vector Cn, would be Ca plus half of AB. And we want to link these end to end to end and end up with a zero. So I'm going to say AL plus BM plus Cn, and then I'll put these added together. So I'll have AB plus half BC plus BC plus half CA plus CA plus half BA. So I simply substituted in these three statements in for AL, BM, and CN, because I want to see what happens when I add these three together. If if something makes a triangle, they should add up together to get a zero, because I should end up back where I started. So let's see if we do that. I have like terms here. AB, oh, I typoed. This should be a BA right here. BA, typo. So I end up with 3 halves. Well, actually, do I? Let's see. Let's make sure I wrote that incorrectly. So I have AB plus half BC. I'm just checking my steps here since I typoed. CA plus half AB. To get from C to N, I'm going a CA plus half of AB. The reason I knew something was off is because I knew that when I needed to add them together, I needed to end up with AB here and here, and that wasn't happening. So I can add together the BCs and get 3 halves BC. I can do the same thing with CA and get 3 halves CA. Well, I can factor out that 3 halves. And so here's what I get now. I have AB plus BC plus CA. But if you look back up here, AB plus BC plus CA takes you back to A. So this is really just AA, which we know is the zero vector. So we end up getting 0, which proves that this forms a triangle. So therefore, AL, BM, and CN can form a triangle. Each problem is going to be a little bit different in terms of what they're asking you to do, but they all have the basic structure of using those different rules that we know from earlier in order to solve and work out the proofs. Okay, that's it for now.